its, bits and qubits. Welcome to Topcast for a bumper double episode. I haven't done this before, but I'll be releasing this podcast in two parts. Well, of course, I often release multiple part podcasts, but if plans don't completely go astray, the first part will come out followed very quickly, within a few hours, perhaps at most a day, by the second part. What I'm doing here is discussing primarily, the primary reason for doing this particular episode is to discuss a paper by David Deutsch called It from Qubit. But as I will explain, It from Qubit has a bit of a history, and one of the parts of its history is entailed in the work of John Wheeler, physicist who inspired David Deutsch. David Deutsch says this himself, by the way. Wheeler wrote a paper that I'll come to, which promoted an idea which came to be known as it from bit. And so David's riffing on that, saying it from qubit. The podcast is in two parts because originally when I was putting this together, I thought I'll just do one big episode. That's fine. But it became so large that there became a natural dividing line between me discussing the history of it from qubit and the paper it from bit. That's all in part one, which is what you're watching now, and discussing it from qubit proper. Perhaps you only want to listen to the stuff that's about David Deutsch. Well, you might think you'll just jump to it from qubit, but believe me, if you are a fan of David Deutsch, you will want to hear a lot of the content here in It from Bit because we talk about one of David's intellectual heroes, and not only the history of the author, who is John Wheeler, but also, I guess, the philosophical and in particular, scientific motivation that David Deutsch has in correcting what I would say are errors in understanding physics and indeed epistemology that might be there in Wheeler's work. And there's a lot to respect in Wheeler's work. Of course there is. And as I will come to, deservingly is Wheeler a hero of a great many physicists. So that's just the introduction for today's episode. Today I'm going to be discussing the fundamental nature of reality, insofar as we can know it. Or can we know it? Have some physicists in the past presumed to know what the fundamental nature of ontological final reality is? What does David Deutsch have to say about this? Well, he did write a paper that goes by the same name as the title of this particular podcast, It from Qubit. But it has a historic lineage, an ancestor paper if you like, and we're going to be discussing both of those today. This paper by David Deutsch in particular that I'm going to be focusing on eventually goes to the very limits of our knowledge, even to the limits of what it is possible to know and the very possibility of, I suppose, knowing it all, of having final theories. And he'll have some remarks to say about those final theories towards the end of his paper, upon which I will have some remarks. But you regular listeners, well, you know what we think around these parts when it comes to the open-ended stream of knowledge that's implied here. More than that, required by the optimistic view of people and explanation creation. So all of that implies something about the possibility of having these final theories all wrapped up in a neat little package. This paper, It from Qubit, was published in 2002, and so it predates the beginning of infinity by 9 years, and it comes about 5 years after the fabric of reality. Here, I guess, and this is purely a guess, mind you, I have not directly talked to David Deutsch about this particular issue. It's reasonable to assume David is getting down into the technical weeds, the basics of what is known about physics in order to extract out what the deepest messages for us, in terms of epistemology, really are. What can be known? David's work in the beginning of infinity, and subsequently on exactly this issue, how there is no wall of progress before us and how we can come to know reality ever better, even if we can never hope to know reality directly and once and for all, does not come out of nowhere. That whole vision of reality and knowledge doesn't come from nowhere, but nor is it an axiom. It comes from careful thought about the implications of our best explanations. But all of our best explanations must be understood in their own terms. And the deepest explanation we have of the physical world is quantum theory. Well, actually, that's only to a first approximation, because, of course, David was the one who mathematically unified what was the purely mathematical theory of computation with the physics of quantum theory, and so properly considered, quantum computation is the deepest theory we have, as it entails both quantum theory and computation. And because it entails computation, it entails epistemology, and if it entails epistemology, it may even entail what it's possible to know that we should do, which means it entails morality, and so quantum computation encompasses quite a lot, and the fundamental unit of quantum computation is the qubit, and so that is why we're going to see that the qubit plays this fundamental role in what we know about the fundamental nature of reality as we understand it. And what does quantum computation, that physical theory, imply about physical reality and our ability to know about it? We get answers to this in the beginning of infinity. We get answers to it in the fabric of reality, for that matter, and we will come back to that later. But you could also consult my series on Chapter 9, Quantum Computers, from the fabric of reality for that. So what this paper is doing for a die-hard fan of David's work like me is take what is there in the fabric of reality and go even further. Rarely have I been so excited to present you with a paper of David's. This is in the same vein as the paper that I discussed once upon a time about David's, titled On the Logic of Experimental Tests. And there, I kind of extracted out the more difficult physics parts of it and to present the content that was there for the non-physicist. I'm doing exactly the same here, because it from Qubit is physics heavy in places. And so we're just going to extract out those bits. We're going to talk over the top of them, explain what we can't actually distill out, and focus on the epistemological and broad scientific and perhaps even philosophical lessons that are contained therein. But before we get there, we need to talk about it from bit. It from bit is like the grandfather paper of it from Qubit. And it was written by someone else altogether. It wasn't written by David Deutsch. This paper that I'm going to spend most of the podcast discussing, it from Qubit, appears as a chapter in a book. That book is rather modestly titled Science and Ultimate Reality, and it is edited by two other intellectual heroes of mine, John Barrow, a physicist and cosmologist who unfortunately passed away in September of 2020, so relatively recently at only 67. Barrow won many big prizes in physics and in science. He won the Templeton Prize, the Dirac Prize, the Michael Faraday Prize, the Dirac Medal, among many others. He was a hero of mine because of the books he put out, not least of them, The Anthropic Cosmological Principle. That's the name of a book. And that is the big tome in work on the fine-tuning of the constants of nature, which, of course, I've concentrated on a fair bit on Topcast. He wrote that book with the great Frank Tipler. It really set the stage for all future discussions on the topic of the fine-tuning of the constants of nature. And, well, go back to my episode on fine-tuning from the beginning of infinity for all about that. And he wrote another book on the same topic, simply called The Constants of Nature later on, as well as many others that I haven't read, unfortunately. I should say, I disagree with almost all the conclusions he draws, but this is why I find him an important thinker on these topics. He did not endorse, for example, explanatory universality. He possibly didn't even know about it. He did seem to hint at strong evidence for a creator and thought there was merit in intelligent design, seeing fine-tuning not merely of the physical constants, but also he saw fine-tuning even in chemistry. But the point is, he articulated all of that very, very well. So he was an editor of this book, Science and Ultimate Reality, alongside my other great hero, Paul Davies. Professor Davies is always hard to pin down on what he really thinks about anything. I don't know if this is a vice or a virtue, but there it is. Does he think there is design in the universe, or just the appearance of design? Is there a God? He's kind of cagey on all of that. But his books, of course, are something like the gold standard, I would say, in popular science. In particular, popular physics and cosmology writing. Now remember, I'm saying that because I do not regard The Beginning of Infinity or The Fabric of Reality as popular science. But if you force me to put them into that category, then I'll say they're the platinum level exemplars. Paul Davies is, I guess, the most prolific living author in that field of popular physics and cosmology books. Like John Barrow, he's also won the Templeton Prize and the Faraday Prize. And I think he's won many writing awards as well that tend not to get listed in his more professional bios. Davies is also that prized kind of science communicator that does not make big claims that have no basis in reality about things we cannot know. He's not a prophet, and therefore he doesn't tend in the direction of pessimism. He's a clear speaker and writer and just says how it is and what it all might imply, rather than saying, we're all definitely doomed for reasons X, Y, and Z, which is kind of de rigueur and fashionable at the moment to do. My own theory is that this is all part of British intellectual culture, and it's only when they let those people over there on the other side of the channel influence their thinking too much that the academics at Oxford and Cambridge and so on begin to go wrong. It's just a gentle jibe, don't cancel me now. So in this book, and I'll say the name a third time, Science and Ultimate Reality, these two authors, Davies and Barrow, come together, and apologies to the third, who, well, I would be underselling things if I said I am less familiar with him. I don't know him at all. I had to look him up, but he's another genuine physicist. He's got a Closer to Truth page, and he has interests in everything from planetary science through to theology, and once worked for the Templeton Foundation. And so, well, there you go. He leans heavily into the Christian worldview. Okay, now, why bother beginning this podcast with any mention, indeed, of these particular authors now at some length? Well, because we've got big names as editors compiling a book where the contributors literally are a who's who of the physics world. We've got chapters in here by Freeman Dyson, Bryce DeWitt, Anton Zeilinger, Andre Linde, Max Tegmark, Lee Smolin, and even the theoretical biologist Stuart Kaufmann, among others. Many others, including, of course, David Deutsch. And what are all these luminaries gathered together in this particular book for? To honour their hero. There's someone else? Yes, the physicist's physicist, John Wheeler. Now, if you don't know of John Wheeler, then you should. In preparing this episode, I thought already that I had some background on John Wheeler, but I'd really only just scratched the surface. This man had a truly astonishing life. He passed away in 2008 at age 96. He worked alongside the likes of Bohr and Einstein. He co-authored a standard text I used for a full year at university, which was this one, Space-Time Physics. Still, I think the best introduction I know of to the field, with even some glimpses into general relativity. It's mainly about special relativity. But never mind that. He co-authored the book on general relativity simply titled Gravitation, alongside Kip Thorne. This book always terrified me. 1,300 pages of general relativity. It dwarfs other physics texts. I mean, even huge undergraduate physics texts, which serve as an introduction to multiple fields from classical mechanics, thermodynamics, electromagnetism, when they're filled with text, images, exercises, examples, solutions, etc., they're huge tomes, but gravitation dwarfs them all. It's just one single part of physics that it focuses on, general relativity. Even the Bible, Old and New Testaments together, only has about 1,200 pages, so it's bigger than the Bible. And the Bible had multiple authors and was written over the course of millennia. This was the work of a couple of men over some period of years. Absolutely epic. Why am I going on about that? Because that standard text, Wheeler in particular, has formed the basis of the education of many of the big names in physics when it comes to general relativity. Right, so he's an author and expert on general relativity. Anything else? Not merely an expert on general relativity. He has been credited with reigniting interest in general relativity throughout the entirety of the United States after World War II. He worked on both fission and fusion, solving key problems in the Manhattan Project and also on hydrogen bombs as well. But really, putting aside all of his scientific accomplishments, lengthy as they are, working on the Manhattan Project, developing the hydrogen bomb, okay, both were big collaborations. He touched on many areas of general relativity and quantum theory, including quantum information theory. Consider his list of PhD students, the people he mentored. I doubt anyone ever can compete here. Let's go through just some of the names. Hugh Everett. He mentored Hugh Everett, the guy who first figured out the multiverse. Richard Feynman. I don't need to do anything else but repeat his name. Kip Thorne, perhaps the world's greatest expert on black holes. Jacob Bekenstein of the Bekenstein bound and black holes have no hair fame. And of course, although David Deutsch was not a PhD student of Wheeler's, David does credit Wheeler as one of the two physicists, alongside Dennis Sciama, as personally influencing him. See this article for more on that. So that's Wheeler. And this book is dedicated to Wheeler and inspired by him. All the chapters are connected to the work of John Wheeler. That is the effect this man has had on physics. This is a channel inspired by the work of David Deutsch, his own ideas and associated ideas. So here I talk about Popper and Feynman, Enlightenment figures, ancient philosophers, and when they come up, other physicists. So here we have a physicist who has himself personally inspired David Deutsch. So it's well within the theme to talk about him right now. Now, in particular, John Wheeler was not only a highly accomplished physicist who did physics, there's some redundancy for you. He was a physicist who also went deep into the implications of physics for other fields, in particular epistemology and metaphysics, though he might not have used those terms exactly and they don't appear to crop up in his writings very often. But before I get to the point of today's episode, which is to discuss David's paper, we have to discuss at least part of that paper that inspired David's paper. That is the paper by Wheeler actually titled Information, Physics, Quantum, The Search for Links. And it was published in 1989. Here it is. And it's in this paper that Wheeler most formally outlines what is known as his it from bit thesis or doctrine. The it from bit claim he made in here inspires at least 4 of the chapters in this book alone. And it's kind of law in the culture of fundamental physics now. Wheeler was the first to coin the phrase it from bit, and it has been used and repurposed ever since. So what's it all about in overview? Well, in my words, it refers to the physical world, all the its that are out there, from particles to pear trees, porcupines and planets, and bit from binary digit, and that's about information. So in other words, the physical world arises out of information. That's what those 3 words mean, it from bit. That's quite the claim, that the physical world comes out of information. And as I'll argue, in a sense, it's not entirely originating with Wheeler, because this idea that you get the physical world out of information, which itself is not physical, goes back at least to Berkeley, as far as I know, and perhaps even to Plato. It's a form of idealism, insofar as whether or not Wheeler thinks that information itself is physical, which is something that David Deutsch thinks is physical. And we'll come to that. We'll see that distinction later on. I don't want to ruin too much of the punchline here. But whether Plato had some idea like this or Bishop Berkeley had some idea like this, of course, Wheeler is going to be far more scientifically and mathematically precise. And we'll have a look at, well, certainly one of his examples that try to explain this perspective. It from bit means that information, or the attempt to find information, determines what its there are. Not what its are merely found, but in principle, what is out there in some sense. This leads to for him, particularly strong form of the anthropic principle. Let's just go over the anthropic principle for a moment. There are various formulations of it, some entirely uncontroversial and some, well, listen for yourself. Firstly, we've got the WAP. WAP. If you don't know why I'm laughing. Well, you can look up WAP in Google, or perhaps not. Anyway, WAP, that's the weak anthropic principle. That's the form of the laws of physics. That's the form of the anthropic principle that says the laws of physics must be consistent with our existence. That's logic, okay? That's straightforward, basic logic, that we exist, so therefore the laws of physics must be consistent with our existence. Okay, that's the weak anthropic principle. No one has any objection to that. It barely even deserves to be called a principle. It's logic. Next we have the strong anthropic principle. The strong anthropic principle says that the laws of physics have the form they do, so we will arise in the universe. Or at least that life will. The laws don't just allow for life, they are set up or designed so that life arises. Now, why would they have this form to ensure that life or intelligence, us, arises? Well, that question is not answered by the strong anthropic principle, but it seems to be an argument for intelligent design or creationism, something like that. A form of the strong anthropic principle, also called FAP, the final anthropic principle, is that life itself determines the laws of physics. How would that happen? Well, near the end of time, life, in the form of conscious explanatory entities like ourselves, want to ensure their own existence. So what they do is they reach back in time by some mechanism yet to be discovered and affect the Big Bang so that conditions are right, so that the universe will become biofriendly, so that they will arise in the universe, so that they can reach back and change the laws of physics such that they arise in the universe. Some people call this the completely ridiculous anthropic principle, CRAP. And if you know what FAP means, FAP, well, FAP might be even better than crap. Anyway, Wheeler's not talking about those specifically. He's talking about something else, something called the participatory universe, or the participatory anthropic principle. The idea here is that what information we choose to seek out, what observations we make, determine what physical stuff happens or is out there. And so this determines the structure of the universe, us as observers determining what exists out there in the universe. The observer plays a deterministic role at the foundations of physics. Long-time listeners to Topcast will know my thoughts about that, but this is Wheeler. So we can't dismiss Wheeler in the same way we can dismiss some crystal-wearing healer claiming to use quantum harmonics to find the resonant frequency of your cancerous tumour. Wheeler has good reasons for trying to explain the world in this particular way. I still think he is wrong. Grounded in science though he is, one of the most knowledgeable people on physics to have ever walked the planet, grounded in rationality and reason. And, well, let's just read what he has to say about this, and then I'll have some remarks on, well, why I think he's wrong. The abstract from Wheeler's paper reads, quote, "This report reviews what quantum physics and information theory have to tell us about the age-old question, how come existence? No escape is evident from 4 conclusions. 1. The world cannot be a giant machine ruled by any pre-established continuum physical law. There is no such thing at the microscopic level as space or time or space-time continuum. 3. The familiar probability function or functional and wave equation or functional wave equation of standard quantum theory provide mere continuum idealizations and by reason of this circumstance conceal the information theoretic source from which they derive. 4. No element in the description of physics shows itself as closer to primordial than the elementary quantum phenomenon, that is, the elementary device-intermediated act of posing as a yes-no physical question and eliciting an answer, or, in brief, the elementary act of observer participancy. Otherwise stated, every physical quantity, every it, derives its ultimate significance from bits, binary yes or no indications, a conclusion which we epitomise in the phrase, it from bit, end quote. Some big claims are being made there. There is no such thing at the microscopic level as space or time, or space-time continuum. This is the writer of the most important text on general relativity, one of the greatest experts to have ever lived on general relativity, saying that space-time itself doesn't exist at the microscopic level anyway. What do we say about that? He's looking at a future theory that is quantum, that is going to show that general relativity in some sense is quantized. He has one way of doing this in this paper, kind of, it hints of it, but to presume it will happen is an article of faith. It's not science yet. But this paper is not a typical science paper. This paper skirts with metaphysics and ultimate theories about the nature of reality very well. But what you can also gather by reading just the abstract there is why David Deutsch would be inspired by a man who wrote in this style on these matters. And I can readily see why Wheeler reaches these particular conclusions, because he seems to me to be unconstrained by knowledge about knowledge about people, knowledge about error and fallibility and so on. I'm not saying he's an ignoramus. I'm not saying he was unaware of such things, though perhaps he was. I just think that he had a different philosophy and a different view, which was mistaken and led him into some mistaken conclusions. This happens to the most brilliant people in the world, and he is proof positive of this, I would say. I mean, he was aware, very much so, of the many worlds interpretation. But my feeling is, those more expert in this might want to correct me on this, but my feeling is, just listening to the man talk about it, he did not understand the many worlds interpretation, despite the fact he was aware of it. And he taught Everett. But, you don't need to take my word for it. You can listen to the man in his own words right here. Here's a YouTube video of this. Okay, so let me just play this here. I'm always reticent to play things like this these days because I get copyright strikes. Even though you're supposed to be able to comment on things for fair use reasons, you can have all the lawyers in the world. The problem is YouTube automates copyright strikes, and there is no one at the other end of the email when you send things. And so the problem is that me wanting to comment on things like John Wheeler here, this is an important historic document, really. Me wanting to comment on this runs the risk of my video being taken down altogether. But let's try this experiment. So we're going to play what Wheeler himself says about his own student, Hugh Everett's theory of the multiverse.
I can recall Hugh Everett's thesis and how I spent most of a night with him going over, trying to word it in a concrete way. But the ideas in the thesis were so strange to many people that they provoke strange names, and particularly produced a strange name, the many-world interpretation of quantum mechanics.
And that's kind of a fair enough criticism, of course. You don't need to call this multiple worlds, and it does evoke in people a misconception about what's going on, this idea of parallel realities that don't interact, but of course we understand that there is this thing called interference. And as David Deutsch says, of course, this idea of multiple realities or multiple worlds or universes, call them what you like, they're emergent parts of the more fundamental thing. The fundamental thing being the multiverse. Just physical reality is what exists. And you could partition this up into groups, conveniently for whatever purpose you might have, into things that you call universes or things that you call worlds. But even then, it still leads people to think, well, when you're talking about a universe, what you're talking about is this whole thing that is, 13.8 billion years old, that has this particular diameter and so on and so forth. But that's not quite true. After all, all you need to do is an interference experiment that is confined within a black box somewhere, like a quantum computer, and that constitutes a universe on this view. This is why this Everettian way of looking at quantum theory is sometimes hampered by the language itself. People just balk at the idea, and yet it is the simplest idea. And so Wheeler is right to say that it gives rise to these strange terminology. But then again, all interpretations, so to speak, of quantum theory, just quantum theory itself, gives rise to some strange ideas. Particle physics, for that matter, gives rise to some strange terminology, as does astrophysics. He invented the term black hole. Who's he to talk about strange words? All right, let's keep going and listening to Professor Wheeler.
A certain probability that such and such happens, and we'll be in a universe where we see that happening. Or there's a certain probability that something else happens, and we'll be in a universe where we see that happening. Well, isn't that obvious, you could say. Well, in Everett's mathematical formulation, these possibilities were coexisting and could come together and be extinguished. It was only when one got to the point where one had an irreversible active observation that one of these became materialized.
But that's not Everett's view. The act of observation is not the thing that causes the materialization of something. That's the view that he is refuting. He's saying that collapse doesn't happen. That's the whole point. whether the observer is there or not, once a quantum event happens, once there is optionality in the universe, possibility for an electron to go hither rather than thither, or a photon or any other fundamental object, then you have this differentiation. I was watching a thing by Sabine Hossenfelder earlier on about the many worlds interpretation, and she gets it wrong. She talks about splitting of the worlds, which always evokes this incorrect idea. What happens is differentiation. Differentiation of pre-existing class measure of fungible instances of the universe into things that are different, and they can become the same again during interference phenomena, that kind of thing. But what Wheeler's talking about here is the act of observation gets no special dispensation in Everett's view. In all other non-equivalent visions of quantum theory, then the act of observation does have this special physics. It causes the collapse of the wave function. It causes the other realities to disappear. Call it what you like. It brings into actual reality the thing, which is actually more in line with his deeper metaphysics, that observation somehow brings into reality this stuff. But this is not what Everett thinks. Everett doesn't think that observation plays this pivotal role at all. The observer obeys the same physics as everything else, and because the observer obeys the same laws of physics as everything else in the universe, then if physical reality differentiates itself into two possibilities, one where the electron goes left and one where the electron goes right, so too does the observer. Now we have this mystery of consciousness, okay? We are one consciousness, we're not divided into two, and so we can't experience both at the same time, which, by the way, if you watch Sabine Hossenfelder's video on this, she's confused about as well. She thinks that we should somehow have conscious experience of both things simultaneously. No, we don't. We don't understand consciousness. We don't understand the way in which consciousness is related to the multiverse. Okay, there are mysteries everywhere. There are mysteries all over the place. There are always open problems. But this particular problem is solved. This problem about what is the measurement problem, okay? Sometimes called that. What is the measurement problem? What is the observer effect? Or whatever you want to call that. The measurement problem is solved. There is no such measurement problem. When a measurement is made, when a quantum event happens, physical reality differentiates itself into the various options that could possibly have happened. And you observe only one, because you are an observer, you are not observers. Okay, what does Wheeler go on to say?
If there's anything designed to confuse somebody about what quantum mechanics is all about, this does it.
That's so unfair, isn't it? As if designed to confuse, and it's actually clarifying. Oh, I would love to be able to speak to him, and say that the only time I was relieved of my confusion about what's really going on in quantum mechanics was to read about this very theory as explained by his own intellectual descendant, David Deutsch, his own intellectual grandson, if you like. After all, if Wheeler taught Hugh Everett and Hugh Everett inspired David Deutsch, then you have this great lineage, this intellectual lineage. And far be it from me to put myself anywhere there, but I learned from David Deutsch what Hugh Everett was teaching the world. And it was the only thing that made sense. When it came to trying to understand what was going on here, it was not designed to confuse, but quite the opposite. It was designed to clarify, and it is clarifying. All other ideas sound to me to be nonsense. So, yes, that there you go. There's Wheeler on Everett. So that's what he says. He says about the multiverse there. I think he gets the multiverse wrong in saying that, when you observe it, something exists, but that's in fact the opposite to what the multiverse says. It says that the observer has no special physics. The observer doesn't cause things to exist or not exist. It's just part of the physical system. If quantum things can happen and there are observers there, then the observers partition themselves among all the possible things that could have been observed. Whatever the case, perhaps he did understand quantum theory, the multiverse, I should say, but his exposition there wasn't as good as it could be, and he had other cogent reasons for rejecting the multiverse. But take that as read. I think that he didn't have a good understanding of, let's say, conjectural knowledge and the errors of empiricism and fallibilism and foundationalism and so on. For all the misconceptions that a book like The Beginning of Infinity would have cleared up for him if only he had have lived long enough to have read it. You know, the absolute best of us, if we didn't have The Beginning of Infinity, would readily slide into something like Wheeler's vision here. So we should put his ideas here, as expressed in the abstract right there, on the pedestal it deserves to be on. Which pedestal? The pedestal that is the pinnacle of what you will get out of an ultimate conception of reality given quantum theory and information without knowing anything about anything that is in The Beginning of Infinity. For want of another way of expressing this. Without knowing the requisite epistemology, vision of mathematics, understanding of physics, etc. You'll get, possibly, Wheeler's vision. Okay, let's just go back, to that abstract. Look at number 2 there. There is no such thing as the space-time continuum. As I say, this is the man who wrote the book on general relativity. Who am I to quibble? He thinks that general relativity cannot be the final theory of reality. And of course, I agree, but I don't think we can now make any such claim about the existence of the continuum or not. But he does. He says that every physical quantity, every it, derives its ultimate significance from bits, binary yes or no indications. In other words, it from bit. Now, we should see a red flag there. Derives. In what sense is it derived? How is it derived from bit? Is it derived logically? Via some other form of reason? Via the senses? Some other physical effect? Well, we have to wait for David's update. It from Qubit that I'm going to read in short order in order to explain at least some of that. By the way, David's obviously not going to say we derive it, physical reality, in its entirety from qubits. He means something else. And again, let's wait before giving the entire game away now. In the meantime, let's go to Wheeler's paper and pick out some of the gems that are found therein, because there absolutely are gems to be found here. I mean, you go mining and it can be like that. We mine this particular older paper and we find gold and diamonds. There are gems. But mines are dangerous places. They can collapse in on themselves, or you can fall into a great void and pits and people can be lost. So you have to know when you've dug deep enough and how to dig your way out again. As Saruman in The Lord of the Rings said, what is awoken in the darkness here, amongst all of these gems, I would say is a form of foundationalism. The idea you've reached the bottom. And Wheeler was searching for the foundation, the unalterable, unchangeable foundation. And you have also another kind of bottom if you think that you've found that base reality, which is an end to your own progress, which is a shame. But this paper by Wheeler is about many things. It from bit is really just one part of the broader whole. The broader whole includes 3 questions, listed here, 4 no's, and 5 clues, he says. I'm going to focus narrowly, however, just on it from bit. Wheeler says there are 3 examples which serve to illustrate his idea of it from bit, and I'm going to ignore the first 2. They're about photons and electrodynamics and what he calls the Planck area, which is mentioned in the third, but I'm going to skip over those 2 and go just to the third one, because to my mind it's the more interesting one. And it's about something that Wheeler himself named, and many people may not know that this term is due to him, and that term is black hole. Yeah, he coined the word black hole. Now, of course, there were no doubt all sorts of holes in history, many of them people dug in their own gardens, and perhaps when they looked into them, they described them as black, so he probably wasn't the first person to use the phrase black hole. But what we mean is, of course, the cosmological object, the thing whose event horizon around a singularity is known as a black hole. Wheeler coined the term for that object. So what does he say about it from bit and black hole? Well, let's just read him and recall that Bekenstein and Thorne, 2 names that we're going to hear in this little passage here, were among many of Wheeler's PhD students. Wheeler says, quote, "As third and final example of it from bit, we recall the wonderful quantum finding of Bekenstein, totally unexpected denouement of earlier classical work of Penrose, Christodoulou, and Ruffini, refined by Hawking, that the surface area of the horizon of a black hole, rotating or not, measures the entropy of the black hole, thus the surface area, partitioned in imagination into domains, each of size 4h bar log 2, that is 2.77 times the Planck area, yields the Bekenstein number, n. And the Bekenstein number, so Thorne and Zurich explain, tells us the number of binary digits, the number of bits that would be required to specify in all detail the configuration of the constituents out of which the black hole was put together. Entropy is a measure of lost information. To no community of newborn outside observers can the black hole be made to reveal out of which particular one of 2 to the power of n configurations it was put together. Its size, and it, is fixed by the number n of bits of information hidden within it. The quantum, h bar, in whatever correct physics formula it appears, thus serves as a lamp. It lets us see the horizon area as information lost, understand wave number of light as photon momentum, and think of field flux as bit-registered fringe shift, end quote. It's a wonderfully eloquent and powerful passage there about the purpose of Planck's constant, what it can do, sort of poetic explanation of entropy there, and black holes all tied up together. Planck's constant, h bar, reduced Planck's constant I should say, is often quoted in joule seconds. It's a curious thing to think about physically. What's the physical meaning of this thing? It's kind of like the size of the step that you take between quanta set in the universe. So it's the size of how much you go up each time you want to increase the amount of energy of some system. It goes up in multiples of Planck's constant. So from one energy level around a nucleus and another energy level, that's in multiples of Planck's constant. Or equivalently, photons are emitted from atoms, which is basically to say they come in individual types with energies of multiples of Planck's constant. Planck's constant in standard units is 6.6260715 times 10 to the power of minus 34 joule seconds, or joules per hertz. A per hertz or inverse hertz is a second. But don't worry about all that. Notice the fact that minus 34, 10 to the power of minus 34, is a small number, which is why quantum effects are not readily noticeable around us. We live in a world of emergent simplicity, which is classical to some approximation, but technically always actually really quantum. But you need to begin approaching that 10 to the power of minus 34 scale before, Heisenberg's uncertainty principle begins to make a difference to how you specify saying where something is or how fast something is going. And it's only down at those levels where it really makes a difference. The fact that you can't just go up and down in quantities of energy by any arbitrary amount. It's in amounts of 6.626 times 10 to the power of minus 34 joule seconds multiplied by the frequency of your photon. So if your photon is 100 hertz, that's a low frequency, by the way, it's a radio wave, then your energy is 6.626 times 10 to the power of minus 32 joules. Let's not do any more calculations for now. Let's just accept that this Planck number, this Planck's constant, I should say, exists. So we have this number which sets for us the size of the discrete jumps in the universe, in our universe, that are possible to make when moving from one amount of a thing to another, in particular energy in this particular case, as we're using this example. You can't have any amount of energy that you like. The energy comes in bundles, usually called photons, and they occur in these discrete steps, multiples of Planck's constant. That's the quantum. And what he says about there with regards to entropy is nice, don't you think? Entropy is a measure of lost information, he says. So I guess this is also where Wheeler is getting his idea of rejecting the continuum. In other words, in the specific case of the surface of a black hole, but also this is more broadly to do with any amount of entropy, any region of space, really, not just a black hole, but he's talking about a black hole here. Its area specifies its entropy so that it can be imagined to be partitioned into domains, as shown in this picture here, which specify the constituents out of which the black hole was made. So reality in that sense, at the surface of a black hole, can be imagined to be information. This has also got something to do with this holographic principle. And now see that movie Interstellar for more about that, I suppose. That, one of the writers, certainly one of the expert advisors to that movie was Kip Thorne, one of the greatest experts in black holes of all time and student of John Wheeler, which is why some of us really like that movie so much. It also had one of the most accurate portrayals of a black hole ever featured on film. This picture here says symbolic representation of the telephone number of the particular one of the to the power of n conceivable, but by now indistinguishable configurations out of which this particular black hole of Bekenstein number n and horizon area 4n h bar log 2 was put together. Symbol also in a broader sense of the theme that every physical entity, every it, derives from bits. Well, there we go. Now, for me, personally, I don't know why this particular result, profound as it is, generalizes to everything else everywhere in existence for all time. The Bekenstein bound, so called, is about the entropy in any fixed region of space. Okay, but from that fact, existence becomes nothing but information on this basis is quite the stretch. Or rather that all physics reduces to information and there's no physical stuff left. It's all just information. If that is the implication, that seems a stretch. The very notion that, matter isn't matter, that it's information, at bottom, I think that matters. David will go into this when we get to his paper that we're coming to. Anyways, when Wheeler does say imagine, he uses the word imagine there, it's rather telling. Imagine that the surface contains information in the form of zeros and ones. Imagine, yes. Well, let's move on from here to later in the paper because Wheeler writes more about his no's and his questions. We're skipping all of that because I just want to go to the it from bit stuff. So Wheeler goes on to say, quote, let me just reread what he did say and then we'll go on. He's just said, quote, the quantum, h bar, Planck's constant, in whatever correct physics formula it appears, thus serves as lamp. It lets us see horizon area as information lost, understand wave number of light as photon momentum, and think of field flux as bit-registered fringe shift. Giving us its as bits, the quantum presents us with physics as information. How come a value for the quantum so small as h bar equals 2.612 times 10 to the power of minus 66 centimeters squared? Just pausing there, my reflection. So, he's using different units to what I use as standard units. I stick with meters and seconds. He's got centimeters going on here. Okay, fine. And he goes on, quote, as well as ask why the speed of light is so great, as c equals 3 times 10 to the power of 10 centimeters per second. No such constant as the speed of light ever makes an appearance in a truly fundamental account of special relativity or Einstein geometrodynamics. And for a simple reason. Time and space are both tools to measure interval. We only then properly conceive them when we measure them in the same units. The numerical value of the ratio between the second and the centimetre totally lacks teaching power. It is an historical accident. Its occurrence in equations obscured for decades one of nature's great simplicities. Likewise with h bar. Every equation that contains an h bar floats a banner. It from bit. The formula displays a piece of physics that we have learned to translate into information theoretic terms. Tomorrow, we will have learned to understand and express all of physics in the language of information. At that point, we will revalue h bar equals 2.612 times 10 to the power of minus 66 centimeters squared as we downgrade c equals 3 times 10 to the power of 10 centimeters per second today, from constant of nature to artifact of history, and from foundation of truth to enemy of understanding, end quote. Okay, so big claims there, and something I think that is quite technical in places. Time and space are both tools to measure interval, he says there. Then the key point, we only properly conceive them when we measure them in the same units. Okay, so what's this about? This takes some technical physics to try and understand what Wheeler is saying here. So I'm going to take two senses. Perhaps the better idea would have been to ask some proper physicists. But the point is here, with my channel, is that I am trying to explain technical physics concepts to the layperson. I'm trying to be the conduit. So if I don't get this stuff, then the person is clearly not writing for someone with undergraduate or master's level physics knowledge, writing for someone who's got the PhD and above professor level physics knowledge. So this is where I'm being pushed, okay? I think I have a good understanding of special relativity. I think I have a basic understanding of general relativity. And this is, of course, the greatest expert possibly who's ever lived in general relativity, explaining aspects of general relativity. So, as I have said, who am I to question what's going on here? But what I take away from this here is something that just comes straight out of special relativity, really, called the space-time interval, is that space and time are not fundamental. That's what general relativity, that's what special relativity are telling us. That if you move through space, your measurements of clocks externally to your frame of reference change, which means literally time slows down if you're moving through space. And similarly, if you're moving through space, then other spaces outside appear to be length contracted, so we say. Space and time are intimately tied together into this one unified fundamental thing, space-time. So we measure space and time, space-time, either in units of seconds or meters. These are interchangeable in relativity. It just depends on what you're doing. For example, a photon gets everywhere, absolutely everywhere, and I know this is hard to accept, you just have to apply the equation, but it's simply a fact of the matter. A photon in its frame gets everywhere instantly. Photons travel at the speed of light. And when you travel at the speed of light, all lengths appear contracted to zero to you. Time appears not to pass at all. You just get from here to there instantly, no matter where you're going, from one side of the galaxy to the other. Now, of course, if you're watching this photon go from one side of the galaxy to the other, you see that it takes 120,000 years, whatever the diameter of the galaxy happens to be. These are hard things to get your head around. And this is why relativity is called relativity, because moving objects appear to have their time moving slowly. Moving clocks appear to tick slowly, is what we say. Time appears to be relative. Space appears to be relative, hence this term relativity. It appears as though nothing is constant. Well, okay, the speed of light is constant, and the space-time interval is constant as well. Okay, the space-time interval, which is a more complex thing than either simply the space and the time. Okay, the distance in space-time, that is constant for all observers all the time when something is moving. But I'm quickly getting into the weeds of special relativity, and we don't want to turn this into a lesson on special relativity. But what I find here with what Wheeler is saying is that, on the one hand, he's just saying right there, look, space and time kind of don't even exist in some sense. There's a deeper thing. Now, just because there's this deeper thing called space-time doesn't mean the emergent thing doesn't exist, is the first thing I would say about that. You can come to a deeper understanding of it. Space and time can still have their emergent existence. But all right, let's go with Wheeler and just say the best explanation, this would comport with what Deutsch says about what it means for something to exist at all, is that does the thing feature in our best explanations of reality? Okay, well, space-time features in the explanation of reality that is general relativity. So it exists by that measure. That's the deeper thing, space-time. We have that explanation, general relativity, special relativity, that says that space-time exists. Okay. But then again, on the other hand, Wheeler has one of the whole purposes of this paper, the thesis he's putting forward, is to deny even the existence of space-time. So never mind just space and just time, which he's denying have reality. He's saying even space-time doesn't have reality, because space-time is merely an it, after all. He wants to say it's all actually bits, even space-time. He wants to eliminate the speed of light and Planck's constant from fundamental physics, saying they are a kind of artifact. And well, this is where this idea of natural units comes in, which physicists use all the time, rather than say the speed of light is 299,792,458 meters per second, which is what it is. You can just set it in your equations as c equals 1. Well, why not? You can call that speed, which is a constant, you can call it what you like. So set it as 1, and then it sort of effectively kind of disappears from your equations. Wherever it appears, wherever that constant appears, it's now just the number 1. These are called natural units. And you can do the same with, Planck's constant h. Just set it to the value of 1, and it appears that they disappear. The particular value that you had, this complicated number, 299,792,458 meters per second, is an artifact of history, if you like. That's what he's referring to, and it doesn't need to appear there. But I don't know why this arbitrary setting of units for convenience which is the way in which we measure a thing, should imply much about the thing itself. But Wheeler does take that step, that a unit of measurement becomes suddenly a fundamental part of reality. And for him, it means you're getting the its from the bits. That seems like assertion to me, but I think I must understand him. He's Wheeler, and who am I after all? I agree, though, with his final sentiments there, that making a big deal of what numbers we express these constants in, whether it's centimetres a second or metres a second or miles per hour or whatever for light speed, like I say, that's an artefact of history. You can just call it one. But his deeper point escapes me, that any of that is physically significant, let alone ontologically or metaphysically significant. It tells us something deep about the ultimate nature of reality, rather than just something about the theory that we're using to explain reality and how we can change the units for the purpose of convenience and for teaching, as he says there. Okay, moving on. Let's see what comes next, skipping bits and pieces here. He writes, quote from Wheeler, fourth clue, consciousness. So remember, he's got all these clues as well. So he writes here, consciousness. We have travelled what may seem a dizzying path. First, elementary quantum phenomenon brought to a close by an irreversible act of amplification. Second, the resulting information expressed in the form of bits. Third, this information may be used by observer participants via communication to establish meaning. Fourth, from the past through the millenniums to come, many observer participants, so many bits, so much exchange of information as to build what we call existence. Whoa, pausing there, my reflection. The observer participants, people, by exchanging information, build what we call existence. Now, on the one hand, this is like comports with what David Deutsch says. Off into the distant future, should we survive and continue explaining the world, creating knowledge, then we come to control reality. This is only possible, not necessary. He seems to be saying it's necessary here. And moreover, that it's not so much knowledge. Knowledge doesn't appear to make an appearance here, but rather this exchange of information, which is really about just observing stuff. Observer participants. Okay, let's keep going. He goes on to say, quote, next paragraph. Doesn't this it from bit view of existence seek to elucidate the physical world about which we know something in terms of an entity about which we know almost nothing? Consciousness. And doesn't Marie Curie tell us physics deals with things, not people? End quote from Curie. Using such and such equipment, making such and such a measurement, I get such and such a number. Who I am has nothing to do with this finding. Or does it? Am I sleepwalking? Or am I one of those poor souls without the critical power to save himself from pathological science? Under such circumstances, any claim to have measured something falls flat until it can be checked out with one's fellows. Checked how? Morton White reminds us how the community applies its tests of credibility, and in this connection quotes analyses by Chauncey Wright, Josiah Royce, and Charles Saunders Peirce. Parmenides of Elia, 515 BC to 450 BC, may tell us that, quote, what is identical with the thought that recognises it, end quote. We, however, steer clear of the issues connected with consciousness. The line between the unconscious and the conscious begins to fade in our day as computers evolve and develop, as mathematics has, level upon level of logical structure. We may someday have to enlarge the scope of what we mean by a who. This granted, we continue to accept as essential part of the concept of it from bit for Lesdell's guideline. Quote, meaning is the joint product of all the evidence that is available to those who communicate, end quote. What shall we say of a view of existence that appears, if not anthropomorphic in its use of the word who, still overly centred on life and consciousness? It would seem more reasonable to dismiss for the present the semantic overtones of who and explore and exploit the insights to be won from phrases communication and communication employed to establish meaning, end quote. Well, he's quite prescient there, talking about computers and how we might need to enlarge the scope of what we mean by a who. Yes, artificial general intelligence there. But there's so much there, there's so much in that paragraph there, that I find a mix of both the sensible and a dalliance or a dance with a relativist kind of poetry. Especially that stuff there about the line between the unconscious and the conscious begins to fade. That's unclear to me. He talks about computers evolving, so, as if just by gradual increase in complexity, suddenly you get consciousness in some way. So that kind of what I would say is a trope. Not back in these days, but these days it would be. Back in those days when Wheeler wrote this, certainly not a trope. That would have been kind of a new idea. But now certainly a trope. That increased complexity means higher likelihood of intelligence, something like that. Let's go to the conclusion that Wheeler writes here. Conclusion. Quote, "The space-time continuum, ? Even continuum existence itself, ? Except as idealization, neither the one entity nor the other can make any claim to be a primordial category in the description of nature. It is wrong, moreover, to regard this or that physical quantity as sitting out there with this or that numerical value in default of question asked and answer obtained by way of appropriate observing device. The information thus solicited makes physics and comes in bits. The count of bits drowned in the dark night of a black hole displays itself as a horizon area expressed in the language of Bekenstein number. The bit count of the cosmos, however it is figured, is 10 raised to a very large power. So also is the number of elementary acts of observer participancy over time, of the order of 50 billion years. And except via those time-leaping quantum phenomena that we rate as elementary acts of observer participancy, no way has ever offered itself to construct what we call reality. That's why we take seriously the theme of it from bit." End quote. Wonderful. So my reflection on that, in part, is this is one of, certainly in his day, the greatest expert on general relativity, I would say. Possibly exceeded by his own student Kip Thorne later. And of course, people continue to learn more and more today, but of all time, John Wheeler, one of the greatest ever expositors and developers of general relativity broadly. Now, if you're in that position, you are one of the greatest ever, then you want to go beyond. And so I can readily imagine that, because general relativity regards the continuum as fundamental, space-time as being a fundamental part of reality, that's the fundamental thing that general relativity is trying to explain, the space-time continuum, then in some sense Wheeler is biased. Being an expert in that area, he wants to go beyond it and say it's not fundamental in any final sense. Now, I agree that it can't be fundamental in any final sense, but it is fundamental as far as we know. Should we expect it to be quantized in the future? I don't know. I don't know if we should expect that or not. I don't know what comes next. Perhaps it is another theory containing a continuum. Well, perhaps if it does get quantized, then a successor to that theory, the successor to the successor of general relativity, becomes a continuum again. Who knows what goes on with our deepening understanding of physical reality. But there's a bias inherent here. The bias is that it simply must be the case that the space-time continuum is succeeded by information which is the final ultimate theory of reality in some way. All about that black hole Bekenstein number example that he talked about earlier. Something comes after the conclusion in this paper, by the way, the acknowledgements. And whose name should appear there? Well, of course, among many great luminaries is David Deutsch himself. David Deutsch acknowledged as an inspiration here for Wheeler, as Wheeler was an inspiration to Deutsch. So this is very nice, isn't it? But now, finally, we get to the meat of the matter. Finally, it is time to discuss it from Qubit. So let's call that part 1. It from bit. And simultaneously, I'll publish these 2 episodes together. I'll just split them up so that you're not forced to listen all in one go. We'll have the second episode, it from Qubit. So that's up next.